The 10-ton Orbital Milestone. SpaceX is currently preparing to move 10,000 kilograms of liquid oxygen between two Starship V3 vehicles in low Earth orbit, a mission that requires solving a fluid dynamics problem most engineers have only seen in simulations. Last month's successful Flight 12 verified the new high-voltage recirculation hardware, but the upcoming ship-to-ship demo is the first time we will see if SpaceX can maintain the necessary pressure differentials without inducing massive gaseous cavitation. While the marketing focuses on moon landings, the real engineering hurdle is the transition from internal tank-to-tank transfer to a multi-vehicle belly-to-belly docking sequence. This test is the literal gatekeeper for the Artemis 3 mission profile, and the physics of moving subcooled methane in microgravity remains the project's highest technical risk. The settling problem. In microgravity, cryogenic propellant does not sit at the bottom of the tank. It clings to the walls and floats in massive globules, which would destroy a pump if ingested. To move 10 tons of fluid, SpaceX must use ullage motors to provide a constant 0.01 g acceleration, effectively creating a fake floor to settle the liquid over the transfer valves. If the acceleration vector drifts by even a few degrees, the fluid sloshes, introducing gas bubbles into the transfer lines and causing a thermal shock that could rupture the plumbing. Unlike the internal transfer on Flight 3, this ship-to-ship maneuver requires two vehicles to coordinate their RCS thrusters perfectly to maintain this artificial gravity for the duration of the flow. Any interruption in this settling thrust makes the transfer impossible. V3 Recirculation Loops. The debut of the Starship V3 architecture introduced an electrically actuated cryogenic recirculation system designed to prevent the catastrophic flash evaporation seen in earlier tests. When -300-degree liquid oxygen hits a transfer line that has been sitting in direct solar radiation, the fluid instantly boils, creating a vapor lock that stops the flow. The new V3 loop continuously cycles subcooled propellant through the transfer hardware to pre-chill the lines before the primary valves open. Some critics argue this adds unnecessary mass and electrical complexity, but without active thermal management, the boil-off rates during a 10-ton transfer would exceed the capacity of the vehicle's pressure relief valves. This system is the difference between a controlled refueling and a high-pressure tank failure. The signal under the noise. The successful execution of this 10-ton handshake proves that the HLS refueling architecture is physically viable, but it also exposes the massive logistical debt SpaceX must now pay. The current Artemis mission profile requires nearly a dozen tanker launches to fill a single lunar depot, meaning the success of one ship-to-ship transfer must be repeated with 99% reliability to avoid a mission-killing launch delay. By focusing on the V3 recirculation loop and precision ullage control, SpaceX has solved the fluid dynamics problem while simultaneously creating a massive operations bottleneck. We are no longer waiting on rocket engines. We are waiting on the cadence of a 10-tanker conveyor belt. The real indicator of success won't be this single 10-ton transfer, but the turnaround time between tanker launches. Watch the Ship 40 and 41 processing speeds at Starbase. That is the only metric that determines if we hit the 2028 lunar window. Subscribe for more